Hello, everyone. Thank you very much for having me today. My name is Stefan Meyering, Sales and Marketing Manager at Corosys. And it's a big pleasure for me to talk to you today with virtual wise, but being in person is still complicated. And so it's great to have these opportunities. Water deaeration is my topic today. It's something that brings us together, as water as a media is the main base where we all work around. Corosys originated from the beverage and beer technology, with the power industry is using water as the main media. So it makes sense, if we take in consideration, to have a closer look to the treatment of water in environmental perspective as well as in economical perspective. So what is the power industry using deaerated water for? The main purpose is preventing corrosion and therefore also eliminate negative effects for non-condensable gases. Those are mainly used for the network and district heating, as well as for boiler feed water. In both cases, whenever there is gases dissolved into liquids present, you will have negative effects. You will have obstacles to turn around, either if there's water being added into a network of district heating. You always have to re-deaerate your water. On the other hand, if you have boiler feed water, you might use your steam, but it is necessary to get rid of the non-condensable gases, in order to make sure you have the best possible heat transfer on the one hand, and on the other hand, to prevent as much of corrosion as possible. Let's dig into the theory of water deaeration, talking about Henry's law a little bit, talking about partial pressure. Looking at the system of water and oxygen, we need about a factor of 1,000 to talk about deaerated water. The solubility level is the maximum, shows us at 10,000 ppb or 10 milligrams per liter, and what we want is 10 ppb or 0.01 milligram per liter. That's a value where we can say that water is deaerated in that manner that nothing can harm the heat transfer processes or have any huge potential for corrosion. There's two main opportunities, two main methods to deaerate water. One is very common in the power industry. It's the chemical reaction with oxygen. And on the other hand, we have the possibilities on the physical side, where we play with Henry's law in reducing the solubility of oxygen. So how is this happening? Henry's law, bring it back into our minds, is the concentration of any gas, in this case oxygen, is described by the partial pressure and the so-called Henry constant. So it's a direct proportional function. So as the pressure on the gas layer above the liquid phase rises, we have an increase of the concentration in the water in the same manner. So what opportunities do we have? We can lower the pressure at a vacuum or at a stripping gas, something which is not oxygen, but also has less solubility in water. Or we can raise temperature, as the Henry constant is temperature related. So the higher the temperature, the less solubility I get, the lower the pressure, the less solubility I get, or by the addition of stripping gas, creating an environment where the gases compete about solubility in water, I also gain less concentration in the equilibrium phase. How do those apparatuses look like? What kind of systems are there in the market? So what we always want is create a contact surface between water and gases phase, which is quite large enough to make it as efficient as possible to deaerate or to decrease the solubility of oxygen in water. Usually the easiest apparatuses are so-called spray degassers, spray deaerators, which require a present stripping gas such as nitrogen or CO2. And by spraying the water in a vessel which is under vacuum, so the oxygen is removed from the water, but not to a very sufficient value, usually less than 100 ppb, not more. Positively can be mentioned it's a compact design. Same way, compact design advantage for the membrane deaerations, but as well here we need any addition of stripping gas. And on the other hand, the water has to be specially treated in order to not damage membranes, or if so, the cleaning of the membranes isn't very easy or cheap. And for that reason, the column deaeration, in our perspective, is something which deserves more attention to be used as deaerator. One point is the high dimension, but on the other hand, as a full stainless steel contact apparatus, it's almost maintenance free, it's completely cleanable, and the counter current flow makes it very efficient. So how is it done in the power industry? Let's take a look at the schematic of this boiler. Usually steam is introduced into the boiler feed water, and a mixture of steam and gas, of such non-condensable gases, is released from the vessel. Of course, this is also a compact design. It's something which is anyway present, so it makes sense to use it. And as long as steam is present, this can be an opportunity to do so. Anyhow, you are losing steam, and it's no actual cold deaeration. So let's have a look at the column. I'd like to dig a little bit deeper into this one. So as mentioned, the principle works on large surface, counterflow, and presence of stripping gas. So the water, cold water in this case, no problem to do so, is brought up to the top of the column, while there is a stripping gas coming in counterflow from bottom to top, which makes it very efficient and easy scalable, of course. So machines between 1 and 100 cubic meters per hour are possible, as well as it's possible to go to a downgrade of the flow of about 50% of the design capacity. If there's any problem, it's still fully cleanable. Inside of the column, you can see such stainless steel structured packagings for the surface creation. Makes it, as mentioned, quite efficient, and also the flow from between water and gas, they don't compete as hard, so it's as mentioned really quite efficient to work with such contact apparatuses. So what brings us into the power industry? I mentioned quite a few times that the presence of oxygen, of CO2 or nitrogen as common stripping gas is needed. The addition of any stripping gas is needed, but nobody has CO2 or nitrogen in the power industry if you won't buy it. So we designed a patented system for the power industry where the actual stripping gas is generated by the incoming water itself. So how does that work? So this brings us to the high vacuum water deaeration. As mentioned, there are several deaerators where you have to add stripping gas, but usually in the power industry, no CO2 or nitrogen is available. If not, you have to buy it. So we designed it for the power industry in that way that the system is creating the stripping gas by itself, namely cold vapor. So how is it working? We are using a vacuum pump and a double stage column, which helps us to decrease the present pressure in the column in that way that water starts to evaporate to a certain amount. And this tiny amount of water is taking over the role to be a stripping gas. So how is it working? We have two stages. The first stage is comparable in its function with a spray degassing. So water is brought up into a vessel with less pressure available. So the first, whatever can be removed is initially removing, and we see water at about 100 ppb entering the second stage. Here in the second stage, pressure conditions are less than the vapor pressure of water actually is. So this means that a small amount of water is evaporating and therefore taking over the role as a cold steam to taking over the role as stripping gas, and then the partial pressure is moving, the partial pressure drop is moving the remaining oxygen to residual values of less than 10 ppb. So the actual environment in the second stage is creating conditions where oxygen isn't very likely to dissolve into the water. So we get totally deaerated water. Here we did some trials at an existing machine, and you can see on the one hand, so the blue line is temperature, the dark gray line is the residual oxygen value, and the light gray line represents the pressure difference between stage 1 and stage 2. And you can see at constant temperatures that there is a relation between one, the flow, and on the other hand, the pressure difference. And as pressure difference is rising up, we also see the residual oxygen values rise up. So for this system, it's very important to have a properly sized capacity for whatever is needed for your heating power plant. On the other hand, to know about the temperature conditions. Both are very important to know, because all we do is play with Henry's law, basically. So the function of the high water deaeration: water is coming in, going to recirculation. Once the oxygen level is okay, the system switches over to go into the network. Yeah, short application example at BEG in Skopje. We've built such unit as a skid-mounted unit for the container, outdoor placement with insulated column, so it's no obstacle to work around things. Yeah, I mean, column height is the only disadvantage, but there are solutions that work out and also represent industrial standard. Yeah, in Skopje, we're using a double screw vacuum pump, so that there's always one for redundancy. It's feeding a heating power network for the city of Skopje, with a deaeration feed of about 30 cubic meters per hour, and of course with less than 10 ppb. So at the end, I would like to draw a conclusion. Of course, deaerated water is something that contributes your corrosion prevention, so nothing to just skip. Deaerated water systems mustn't be complicated or over-engineered. They can be quite simple and easy to handle. Deaerated water systems do not necessarily demand stripping gas, like CO2, nitrogen, live steam, so nothing to buy or to waste. We just can use our cold steam vapor process. And yeah, deaerated water produced by column method can be a cost-effective alternative to chemical deaeration. Also take the environmental impact into consideration if you think about using another alternative method for water deaeration. Yeah, after the video is ready, played. Nochmal. 3, 2, 1. So once the video is fading out in a couple minutes, I will be available in person to take on questions. Yeah. Other than that, check out our contact, our local representative. Thank you very much for listening. Thank you very much for having me, for the opportunity. It's a great pleasure to talk for you. Thank you.